As I mentioned earlier, you can define your own user-defined functions when the functions available in R are not sufficient for your needs. And in this rather silly example, we'll assume that you are repeatedly adding 1 to different things, different objects, and for some reason you would like to, instead of writing something plus 1 and something else plus 1 and something even more else plus 1, you would like to define a function which adds 1 to things. And for clarity, you would like to call this function add1. To achieve this goal, you would write add1, that is the name of the function you would like to define, equals, and then the command function, which tells R that now you want to define a function, and you want to put that function into the object add1, so that add1 becomes an object which is a function. And then within parentheses you provide the arguments that you want the user-defined function to have, in this case only x, and x would be the thing to which you would want to add 1. And after this you write what you want the function to do. In this case, take x and add 1 to it. So by executing this line of code, you create an object add1, which is a function, which requires one argument x, and then returns the sum of x plus 1. So if we try this out and write, for example, add1, 7, we could also have written x equals 7, but we don't have to because there is only one argument and it's obviously x. And in return you get 8. So what R has done here is that it has taken the argument x, given it the value 7, it has added 1 to 7, that is 8, and returned this sum to you. Not very useful, but you get the idea. Something that you also may need to know is that the arguments used in a user-defined function are internal objects. So they are not the same objects as other objects that you create in R. And I'll try to explain what I mean by this. If, for example, you create a new object called x and then puts the value 42 into it, and then use your own user-defined function add1 to add 1 to 2, and you get 3 in return, obviously. Since we have defined the function up here, you know that the argument used in the function is called x, and the sum, in this case 3, is the sum of x plus 1. So you might fear that you have destroyed your x value and changed the value of 42 to 2 instead. But that's not the case, and if you ask for x afterwards, you get 42. So the x object is intact, and the x object used within the function add1 is a separate x. So you don't have to be afraid when you define these functions that you would also have to remember the name of all the objects that you are to use in your script. Now we'll look at a more useful example compared to the add1 function, which may not be very useful in real life. And this example is from my field of expertise, the pharmacokinetic area. And here I define a function called elim, which is used to calculate the concentration of a drug in blood or plasma after a certain time after the drug was administered. This is not necessary to understand for you, but that's the concept. And the formula used to calculate the concentration after a certain time is rather complex. It looks like this, and you would have to provide a value of C0, which is the concentration at the time point 0, And then you need to know the half-life of the drug, which is the time required to eliminate 50% of the drug in plasma. So these are two parameters that you need. And if you have them, you can calculate the concentration at any given time point t following drug administration. And to make things easier, I would like to create a function called elim, which takes this information as arguments and then in return gives me the concentration at the time point of which I'm interested in. So I define that the arguments of the function would be t, and by writing t equals 0, I give it a default value of 0. So if I don't provide a t, then I would get the concentration at time point 0. Then half-life with a default value of 12, and C0, which is the concentration at time point 0, with a default value of 1. And then after defining the arguments, I provide the actual calculation that is to be performed by the function. And as you can see, I have put in these curly brackets here, and that's not really necessary if I am able to provide the entire function in a single line. But if I would have performed more advanced calculations and things, and I would have to use several lines, then I would also have been forced into using curly brackets. One to start whatever the function is to do, and a second one to tell R that this is the end of the function. So everything between the curly brackets is what the function is supposed to do. So I run this line of code, and now I have an object called elim, which is a function. And then I'd like to test it out and calculate, for example, the concentration at the time point 6 for a drug that has a half-life of 2. And as you can see, I don't provide the C0, so it's supposed to be 1 because that's the default value. And if I run this, I get 0.1125. That is 12.5% of the drug is still in the body after 6 hours, if it's hours we're talking about for this drug. Another cool thing about functions in R is that you can plot them directly. If you would like to make a curve showing how the concentration changes over time in, for example, Excel, then you would have had to calculate the concentrations for a number of time points and then plotted these time concentration pairs and connected them with lines, for example. But you don't have to do that in R. You can actually plot the function itself and get infinite resolution, so you don't have to fake any values. And you do this using the curve command. So I write curve, and then I tell R that the thing I would like to make a curve out of is the elim function. And I provide the arguments for the elim, and the first one I really have to admit that I don't know why it has to be done this way, but I have to write x here and just do it because you have to do it, followed by the other arguments. In this case, I define the half-life as 6 and the initial concentration C0 is 80. And since I left out t will become x, so the x-axis will represent the time. And then I also tell the curve function that I want to start at 0 and end at 24. That's the limits of the x-axis. So that's the way the curve function works. And if I execute this command, I get a nice clean curve showing how the concentration starts at 80 at time point 0 and then decreases logarithmically until this level at the time point 24.